This is the New Quantum Era. I'm your host, Sebastian Heisinger. My guest today is Johannes Galatsanos, co-founder and CEO of Diffraqtion, a Boston-based startup building what they call a quantum camera for satellites and telescopes. But before we get into our conversation, this episode is brought to you by Outshift, Cisco's incubation engine. The need for computational power is rapidly increasing in every sector, from drug discovery to material innovation to complex financial modeling. Classical systems are reaching their absolute limits. It's time for a paradigm shift. The answer is a scalable quantum network built on open standards and vendor-agnostic architecture. By uniting distributed quantum devices, you unlock limitless computational power. Learn more about the Cisco Universal Quantum Switch at outshift.com. Johannes Galatsanos came into quantum by a route I find interesting. He spent years building AI and data teams in industry, including running the data and AI group at Novartis, and along the way became convinced that if you were going to bet on quantum, it was better to be on the building side than the applying side. So we went to Oxford, then to MIT, where he ended up co-authoring the inaugural MIT Quantum Index report with the MIT Initiative on the Digital Economy and Accenture. That report is essentially a data-driven map of the quantum landscape, and it means Johannes is one of the few founders in this space who has looked at the entire field from altitude before staking his career on one narrow and frankly underhyped corner of it, quantum sensing and imaging. The technology Diffraqtion is commercializing came out of Saikat Guha's lab at the University of Maryland, where the original DARPA-funded work was aimed at, of all things, finding exoplanets, extracting signal from photons that direct imaging simply throws away. The claim, grounded in quantum Fisher information theory, is that a conventional camera in certain regimes can lose roughly 95% of the information a photon actually carries, and that you can recover a lot of that by processing the light directly in the photonic domain before it ever becomes an electron, before it ever becomes a JPEG. Now, whether that makes this device a quantum camera in the strong sense of the word is a real question, and I'll push on a bit in our conversation. Johannes is refreshingly honest about the gray zone he's operating in, the interplay between quantum information theory, photonics, analog computing, and neural networks that run at the speed of light. We talk about how the current generation works, what the reprogrammable next generation unlocks, and why a backpack-sized CubeSat with a 10-centimeter aperture is a genuinely disruptive proposition for space domain awareness and Earth observation. We also get into something I've been wanting to talk about for a while, why quantum sensing, despite being closer to deployment than quantum computing on many axes, still runs under the radar. Johannes has thoughts, and they come from someone who both has the data and the scar tissue of raising money in the category. It's a conversation about a specific device, but it's also a conversation about how quantum technologies actually reach the world. Here's Johannes Galatsanos. Johannes, thank you very much for joining me. Thanks for your time. I wonder if you could start off by talking a little bit about your origin story, how you got to where you are now as CEO and co-founder of Diffraqtion.
Yeah, thanks for having me, Sebastian. Johannes or Yanis, I'm Greek, German originally, and grew up between the two countries. A lovely island in Crete. Then moved on and did studies in AI in Germany, and after I wrote my thesis in AI back in 2010, which was kind of in the early AI days, and started working in all kinds of AI applications like drones, industrial inspections, automotive automations, and ultimately landed up in building the data and AI team at Novartis, which is a pharmaceutical company. And there spent quite a few years building up a team from scratch that was bringing back data and AI capabilities for the company. And at the time, I got in contact with quantum technologies too, because I was responsible for also looking at innovations and new tech that's coming out. So I got introduced to a few folks that were doing quantum POCs. I looked into it and I tried to map it somehow what we do actually in the company. And it seemed to me that it was quite far away. This was around 21, 22 or so. But I did realize the potential for the upside if you actually build something in quantum versus you're just using it and having like a side project for a couple of years in quantum, right? With maybe 1, 2 PhDs out of 200 people in your team, right? So I thought, why not be on the other side where I actually built this, because that's going to be a massive upside. You just need a bit of patience. So I thought I should go to the best places to find out about quantum tech and where to even spin out some technology like that. So I went first to Oxford and then to MIT. And at MIT, I started working in quantum research for optimization algorithms for quantum for and benchmarking of algorithms for drug discovery specifically. So I wrote my thesis in that too there at MIT. And at the same time, started building the quantum index report, which was basically, again, a benchmarking of all QPUs, and then also looking at papers and publications, patents, and everything that's being released by country, by university, and so on, to kind of keep track of how quantum's progressing over time. And at that time, I met Saikat Guha, who's a professor at UMD, who runs the Center for Quantum Networks, which is an NSF engineering center, actually the largest of its kind in quantum tech. And when I met Saikat, he told me he's looking for aliens. I said, "Hey, that's awesome. How are you doing that?" He said, "Well, I have this really cool camera that can see sub-diffraction." And then I looked into it, and DARPA had sponsored his research for about 13 years in the past, of developing this from TRL 0, so basically from idea or concept, to TRL 4, which means it's already shown in the lab. And DARPA gave us funding for starting the company. So we got 1.5 million from DARPA to kickstart Diffraction, and bring this camera to the market. And in the meantime, then we also raised some funding, and now, we're in Boston, or Somerville, right outside of Boston. I think you've been here recently, and we have now 12 people in the team. Have photonics labs here, both manufacturing capability and testing capabilities, and bringing this quantum camera to life, together with my third co-founder, Christine Wang, who is a Harvard PhD in quantum optics and spent the last 20 years in quantum optics, commercializing quantum optics in dual use cases. And she came from Federico Carpasso's lab. So we have kind of the Harvard MIT ecosystem in one company.
Yeah, that's quite the powerful axis in Boston between MIT and Harvard. Similar sort of axis of brain power that fuels QERA between Vuletic and Lukin's labs, right? Yeah, so it's a good pattern, definitely.
Yes, it is. Yeah, and we love the Boston area too. There's tons of talent here, and for what we do, intersection like photonics, quantum tech, we have them optics, AI, and then space. I think Boston is a pretty unique place, and of course, we all had our connections to the MIT Harvard ecosystem, so it seemed like a no-brainer being in Boston and having this intersection of technologies here.
That's amazing. And so it's a quantum camera that you're developing.
Yeah.
Can you walk us through what exactly are the elements of the camera that are quantum information technology?
Yeah. Maybe I'll start with what a quantum camera is and then ask the second question, why it's quantum, because I get that a lot. All right. So maybe first with the camera itself, what does it do? The camera can do two things effectively. So one is think faster, and the second, see further, and the second is think faster. So it's also in our motto, see further, think faster. Now, see further means that this camera can can see beyond the diffraction limit. The diffraction limit, for those who don't have a physics undergrad or don't remember high school physics, it is the last letter you can read at the optometrist. When they make you read these, the last letter you can read and gets blurry, that's your eye's diffraction limit. Now, that is a physical limit that is bound because of Rayleigh. I mean, that we also call the Rayleigh limit. Lord Rayleigh, who came up with that concept. And the idea is basically that two point sources that come, or let's say two light sources that are very close to each other, they look like the same thing when they're too close to each other at a long distance. So the way to overcome it is you get a bigger lens, right? That's the only way to do it. You get a bigger aperture, and that's how you see further, right? Now, for us,
that's why we end up with telescopes with enormous lenses, right? Yeah,
exactly. That's the concept of why to see further, especially in space where it's interesting, you get telescope. Now, this quantum camera can actually see beyond or extract information beyond that diffraction. And I'll explain in a second how it works, but that's the first benefit. The second benefit is think faster. So what you can do with this is you can run things like classifications, which is kind of a convolutional neural network, like a concept from artificial intelligence for machine vision in particular. You can run that in the photonic realm. And so basically just with photonics without using electronic components. And that allows you to do this whole thing at speed of light and at a very, very low energy consumption. So practically negligible. So that's the think faster part, is like doing inference and classifications at speed of light. So these are the two main benefits and why we built this camera. Now, I'll go maybe to the second part, maybe why it works, and then also explain a bit why it's quantum. So why it works is a simple concept that Saikat was looking into, which is called the quantum Fisher information theory. And that one tells you how much information is contained, in our case, specifically in a photon. And what Saikat found out, and before him also there were a group of researchers that were looking at sub-diffraction imaging. And what they found out is that when you do direct imaging, so when you capture directly the photon and then you convert it either into a film or a JPEG or some sort of digital information, then you are introducing loss. And so you're not extracting the maximum that quantum theory allows you to extract from that photon. And turns out in many use cases like he was looking at, and that's kind of going back to the finding aliens, the use case he was looking at initially with NASA was you are looking at a very faint object, which is a planet that is orbiting a star very far away. It's called an exoplanet. And then that planet, you cannot directly see it because the star is too bright. Normally what you do is the planet goes around that star, and then at some point you see a dip in light and you know, okay, that's a planet about that size. But if it doesn't directly orbit in the same plane, it's very hard to see it. So what NASA was looking at is novel ways of extracting that information, detecting is there really a planet orbiting that star. And when you do a direct image, so when you have a telescope and a camera behind you, take an image of that, you lose, in that case, something like 95% of information from that photon. So you leave 95% on the table, and the question was, right, how do you extract that back, right? Now, part of the reason of why you lose information goes back to short noise. So short noise is introduced when basically the photon is read out, and then an electron is excited, right? And then you get you basically create an intensity, right, matrix, which is then becomes a JPEG, which is basically what a JPEG is. When you do that, you introduce short noise because, right, light doesn't like to be observed, right, as we know. So you have, when you convert the light into electronic information, you lose the information. Now, then he said, okay, how do I do it differently without converting the light to electronic information, right? So you cannot really convert it and capture it into electronic information. That's where you lose.
Right. So I mean, either the visible spectrum or the electronic, photoelectric kind of reaction. Both of those are essentially going from a quantum particle to a classical sort of
Yeah.
level, and there's some loss inherent in that
Yeah.
conversion
Exactly.
from quantum to classical. Okay.
Yeah, exactly. That's another dimension to it, which is kind of explained by the shot noise, practically, right? That you introduce by doing an observation. Right? When you do observation, you introduce loss. That's just a physics fundamental. Um, Now, the alternative idea was, all right, if we cannot observe it directly, right, I cannot convert it. What can I do alternatively? Is I can process that photon, and that kind of is the same concept you use in a photonic quantum computer, right? So you can process photons, right? So you have basically, in that case, you have kind of gates, right? In our case, but what is behind that is um, uh, basically components that you use for quantum computing that could be something like a faceplate or a modulator, right? So these kind of things that you would use, we can actually use to process light directly as it comes to us. Turns out from the scene too. So from what nature created, right? Nature created a scene by sunlight or by artificial light hitting a surface and then getting into your eye, right? That's how you absorb the information. So the quantum state is already created if you want, right? So you already have a perfectly beautiful scene that you're getting. And now the idea is how do you process that to extract some information? And what Saikat found out is a way how to do this in a hardware, so actual hardware. And you can actually process hardware or process this light with hardware in the photonic realm to extract some information. And what we extract, there's different algorithms you can run on this basically computer, if you think of it like a photonic computer. You can run different algorithms. One that we do is counting. So, for example, you can count the amount of sources, or you can count the amount of, let's say, cars on the parking lot, which is interesting for, let's say, trading companies who try to assess how many customers go to, let's say, to Walmart, right? But you can also do classification. So you can say, is that let's say a satellite, or is that debris, or what is that I'm looking at? So you can run all these types of classifications with what we call an optical neural network. So you can actually process light in the same way, or seen in the same way as you process it digitally, but you can do the whole thing fully optically. That's
Yeah.
called
So
a
I mean,
diffractive neural network.
and is that sort of analog computing
Yeah,
or information,
yeah.
or is it truly quantum information processing?
Um, Right. So this is basically where this question gets a little bit trickier on what
Yeah.
exactly you call quantum, what not. Right. So I guess many people would call this in a way because we don't create entanglement and we do not use entanglement in that sense, at least not originally. That means it would fall under what we call like quantum 1.0, right? So some people would call it quantum inspired. So that
Right.
might be another
Right.
term that fits, or quantum 1.0. You can call it quantum sensing if you want. Although quantum sensing again is more, magnetometers, atomic clocks, things like that are mostly used for it. So this kind of falls in between categories. So I don't think it's like a clear stamp, but effectively, what you're doing is you are extracting the quantum limit of information. So that's important. To understand what is the limit, you have to build your device in such a way that it uses quantum algorithms to configure it. So you do use quantum information theory, and actually, Saikat is a professor in quantum information, so that's where it came from. So I think the genesis of it is extremely closely tied to quantum communications and quantum computers, quantum information theory. What we actually run, you're correct, is classic optics or photonics, if you want. So that one would be more akin to an analog computer and analog processing, which we like a lot. So actually, I like that a lot about this because it makes it so much easier, right? So you don't have to dabble with cryogenics, and you don't have to dabble with massive devices. You can actually make it so small that eventually will fit in a cell phone. So you can make it super small, you can make it relatively cheap, and you don't need to bother about cooling it down to some extreme temperatures to work. So I did like that part, that we do not overcomplicate it. but it still works today. So that's the appealing part of it.
Yeah, yeah, yeah. And I mean, as you said, there's all sorts of elements of quantum information. I mean, the Clifford gate set, for example, are easily simulatable. So there's all this sort of gray area between
Yeah,
something that is directly entanglement or superposition dependent
yeah,
and the fully classical realm. There's this
yeah,
pretty broad expanse. And what's really interesting to me about what you're doing is there's a direct sort of parallel in my mind immediately between your device and the early sort of electronic era before universal classical computing was widespread and the microprocessor
yeah,
was a commodity. We had all of these purpose built devices that were using electronics to do signal processing or sensing of some sort, or, I mean, transistor radios, TVs, guidance systems, radar, all of that is sort of, in some ways, I think, analogous to what you're doing. You're using the engineering and the science that's emerging in this category of quantum to make a device that's realizable now, that has specific use cases you can address today. Really, it sounds like, right? I mean, you actually have devices that are operational now, as opposed to more
yeah.
esoteric quantum computing, which is still in the works, as it were.
Right. Right. I think that was a little bit the thought process that I followed when I looked at this. So when I was looking to spin out a quantum technology, I also thought about maybe actually quantum computing, right? Let's find a technology and build a photonic quantum computer or that is slightly better in XYZ dimension, right? And then can beat another one. But to me, again, it was a game of, hey, 5, 10, 15 years, whatever, to be like um, cash flow positive, right, from actual revenue and not just government grants. And that one would be, it's a long journey, right, that you have to go through. And in this case, to your point, yes, this camera already works. It's TRL4, which means it was demonstrated in the lab to have already benefits. Now, benefits to the best conventional camera, actually, in the lab we have like a camera that costs $50,000, and it's like it's liquid cooled, right? Because it creates so much energy and heat because it's so powerful, and that's the best thing you can buy today. We compare to that, and then we can beat it by factors of orders of magnitude better. So that's something that works today, and actually we have the first we call generation zero, but the first camera, which is a proof of concept. We had that up in University of California on the telescope. It's a large 3-meter telescope that the University of California is using near San Jose, and did astronomical tests. So now we keep doing at different observatories these kinds of tests. We have a couple of telescopes here that go on the roof right here in Boston that we can test the initial versions. And these initial versions already beat conventional imaging systems. And that was important for me to pursue something that is really useful today, not just in 10 years, right, beating a conventional technology.
You mentioned not just resolution but speed. Is there some correlation between the speed of processing and the effective frame rate or sample rate that you could potentially produce?
Yeah, so this is where things get interesting because there's no frame in that sense, because there's no shutter, right? So the light is processed at speed of light, basically, as it goes. So as long as you have enough photons, there's always a photon budget where you receive enough photons to trigger something. But as long as you received enough photons from the source that goes basically through and is processed, and you have detected that particular object, you have done the full processing. And that is measured in time, obviously, versus frames. Um, and then the frame in that sense comes when you read it out. So when you have a readout of that camera, so at some point you need to convert it to electronic information so that your machine can do something with this, right? Because otherwise it's just light fluttering around. So you want to convert it at the end. At that point of conversion, you have obviously loss, and you also have basically a time loss, right? Because you're constrained to the power of a processor. Now, interestingly, the only reason we have to do that is because conventional computers are too slow for our camera, but which is funny. But I think eventually, and this is kind of where it will get very interesting, as I'm sure we will find other ways to extract this information and not have this loss introduced. But because it's already processed, really, you already did the calculation. You don't need to really read it out electronically. But if you do, you lose a bit of time. That's where a frame comes in. And but again, as long as you have enough photons, you have an instant recognition of the scene or of the classification. And I can tell you, yes, I'm looking at a dog or a cat or a car or a bird or a satellite. So that's enough.
It's so fascinating too that I think it's worth sort of repeating what you were saying. Essentially, there is no imaging the way humans think of imaging. You're sensing the
Yes.
photons directly and processing the photons directly without the
Yeah.
intermediary of representing it digitally or
Yeah.
chemically in the case of photography or classical photography. Like that's such
Correct.
a interesting. You're basically taking photonic information and feeding it directly into a neural net without
Yeah.
the intermediary step that is really dependent on human biology rather than
Yes.
the information.
Yeah, yeah, correct. Yeah. And I mean, the idea of it, think faster and see further. Our markets that we're going into is initially obviously satellites and space. So we work with Space Force and NASA for applications like when you have debris in orbit that is trying to hit your or might hit your satellite, especially as now millions of satellites go into space. You want to make sure that that's basically safe to operate. It could be, it could be another satellite hitting you. It might be accidental or not. So in all these scenarios, you want to know what's going on in space, right? And there we have the application, which is space-based. But future, a lot of that happens in a satellite onboard processing, right? So you want the satellite, these things fly at 20,000 miles per hour, right, in low Earth orbit. And then you have two objects both flying at 20,000 miles per hour. That you're talking about, massive distances that you have, and then you have seconds to react. So at that point, you want to have onboard processing. So if you first have to take a JPEG, send it
Yeah,
down to an operator, and then the
forget it.
operator
Yeah,
says, by the time it's down, the thing is already blown, so at that point, the accident has happened. So you want to have onboard processing, and the satellite or the machine that is doing the onboard processing has to do it in the most efficient way possible. And converting it into a JPEG first and then having a whole GPU trying to replicate what the heck happened in this JPEG, right? So that is two layers which are actually kind of unnecessary if you think about it, because if you could do the whole thing at speed of light and get an inference at speed of light, why bother doing two conversions and send it back to the machine
you're
when there's no
effectively
point to it?
giving the satellite a photonic sensing device that could, that can sort of round trip through its own logic processing without any
Yeah.
of the intermediaries that are human dependent.
Correct. Yeah. And the machine doesn't need those intermediary steps as long as you have the information extracted, right? They don't care about an image. As long as they know go left, go right, right? Or stay on course. They don't need to necessarily get a JPEG. So JPEG was a little bit of I think, a logical step. And the way I think about it is, humanity always had these logical steps like, okay, first you did, paintings, right? So you had cave paintings, right, in the ancient form, statues. Then you discovered at some point you can put it on a canvas, right? At some point, film. Okay, we can actually take real pictures now of things. And then digital pictures, right? So kind of evolved on imaging. But now the thought is, well, let's go even closer to nature and say, forget about, you don't even need that. The light itself already will tell you. You can process it directly in its most pure form. So I guess, like many things, it moves from digital to quantum, right?
Yeah, it reminds me of I remember reading about the cones or the rods that are configured in a certain way in a frog's eye, where
Yeah.
if a certain pattern gets triggered, their tongue fires out because it's
Yeah.
essentially sensed a fly, and there's no round trip to the from the brain through the optical sensor.
Yes.
It's like photonic
Yeah.
to like tongue trigger basically.
Exactly. Yeah. So actually, we
Yeah.
have, if you go on our website, we have this example with the eye, and actually, the eye has what we call retinal ganglion cells. So these cells are actually, to your point, doing exactly that. So they can process shapes and trajectories. So they have, scientists have taken out, an eye detached from a brain and shown it like shapes, and they could actually react. So they would fire up like neurons. And that is happening way faster than your brain. And for animals, actually for humans too, like if you ever caught a baseball, that was actually your eye, not your brain, doing the thinking, because you need to very quickly grab it. Or if you dropped a fork or something and you quickly grabbed it and caught it, that was your eye doing the thinking, not your brain. That's actually directly tied to your reflexes. So it's a very, that's why we think about it like a quantum eye, if you want, right? Like a better eye for your satellite, for your car, for your robot.
That's really cool. And so you've mentioned a satellite. When I visited your lab, you had a mock-up of what that satellite looks like. It's quite a bit smaller than I think people are used to thinking about with satellites. So it's following the CubeSat format, right? Can you sort of describe what that first device is and when it's going into space?
Yeah. So actually, it's quite handy because it's CubeSat. A CubeSat is basically backpack sized. It fits exactly in a backpack. I know that because I have a backpack with it, and I go to all these conferences to show people the actual product. So it's actually quite handy that it fits exactly in a backpack. But it's pretty small, and the camera itself is 1/6 of that. So it's 10 times 10 times 10 centimeters. So it fits quite neatly into that. And think of a couple of cell phones stacked on each other, like maybe 5, 6 cell phones stacked on top of each other. So that's the size of the camera. Now, that CubeSat usually is sent to space to test a new type of sensor, or an academic group, like a university, might have a little CubeSat program, right? Because they're quite cheap to send to space. They're quite cheap to procure. So that's more like a test bed. Normally, nobody really uses them for effective things to do. Now, in our case, that little CubeSat with a tiny lens, which is only a 10 centimeter aperture, so kind of small lens, that one can, from low Earth orbit, looking back to Earth, see something or classify something the size of your laptop, right? So that's usually reserved to something which is the size of a school bus, right? That's what people think about when they think proper observation satellites in space. If you go to NASA's webpage now, you will see the Roman telescope. That's the size of a small building, right? So at that point, you have like massive telescopes that can actually see things from that far. But those are obviously, special purpose, very, very fine instruments that go up there. But they also cost you like $1 billion, right? Or 100 million to $1 billion, or even more. That little CubeSat cost you 3 orders of magnitude less because it's so small. So in space, the unit economics go a bit wild, right, with size and weight. So if you get something that is this small, in such a small size, that benefit of having that whole thing in a CubeSat makes a lot of sense. And that is also where the see further part really makes a difference. But also the think faster, because the other problem satellites have is they can only, like any machine really, can only process about 1 in 10 images. And that's because of weight and power restrictions at the edge, right? So in the satellite. And that ends up that you can only process 1 in 10 images really and downstream. Now, with this one, because it's constant processing at speed of light, you can process everything and send down small packets of kilobytes down to the Earth. So you also have instant thinking, right? Not just high resolution, but also instant down processing and downstream of information. And that little CubeSat will go up into space. The first kind of working version that actually is useful for something is about 28. Before that, we'll likely have another launch or launches, or like test launches of initial draft versions of the camera, and getting a bit flight heritage, right? Testing the whole system. But the main, the main launch will be 2028.
Very cool. And so, I mean, the on satellite sort of avoidance kind of functionality and the Earth observation functionality, I can clearly see those being, dual use in the sort of the classic sense. You're also, I believe, you're part of the discussions about the habitable worlds which is sort of NASA's next generation of successor to the James Webb Telescope, right?
Yeah.
Is that a similar form factor, or are you thinking something much larger for that particular application?
Yeah, so the Habitable Worlds Observatory is the big telescope, NASA's big planned telescope for the next decade. So they always have these decadal telescopes that are pushing science to the next frontier. The last one was James Webb Telescope, which has produced these beautiful images that you can see floating, at least on my LinkedIn or Instagram, or so you see them periodically floating. Um, and before that, I guess the first one that people really know and might associate is the Hubble telescope, right? So that was kind of the original. The Hubble telescope's floating around the Earth, so it's in low Earth orbit. That has some downsides to it. So the next one is actually coming up in September. It's called the Roman telescope. That's going to create some beautiful pictures and find more exoplanets. So the next one planned after that is the Habitable Worlds. That the research for that was also and the group there at NASA was sponsoring the development of our camera originally in Saikat's lab, and that telescope is going to be a massive telescope, also next to the Roman and the James Webb telescopes that will fly around very closely in Lagrange 2 point. So about, let's say, 4 times behind the moon, basically, if you think about it. And that one will take amazing pictures and find exoplanets. And the camera in that case that we would put in is not much larger than that, honestly. So surprisingly, it's pretty small still. Um, but it will have obviously some much more sophisticated algorithms and photonics and optics in there. That's going to be a next generation, not the current generation, obviously, that we have. But that is going to do a few things. The first, maybe most interesting thing is called coronagraph, where if you look at, if you look straight at the sun on daytime, you will get blind, right? Because it's so bright. But if you and if a plane passes there, you won't be able to see it directly. But if you put your hands against the sun in front of your eyes, so you block it out, you can still see the plane floating, right? So you're not completely blind. It's the same concept. It's called a coronagraph. So you basically block out the sky or the particular star, and then you can look at the exoplanet. So that was the main application for it. And turns out you can correct. So running an algorithm in our device, you can actually correct for very bright sources and look at dim sources. That's called a coronagraph. So we can operate that way purely by processing the light and extinguishing bright sources. So anything that was blinding you, you can extinguish it and look
I
behind.
see.
On the size factor, just to get a reference, our camera that was put in the 3-meter Lick Observatory in California. This was a observatory. It's the size of a skyscraper, really. And then this whole massive light comes through and then goes in a tiny camera. And the camera, actually, if you see it, the chip could fit in your cell phone. So you make a entire, a skyscraper converting into your cell phone sized camera,
Right.
which is for me bonkers, but this is optics, right? So
Yeah. And I mean, all of these different use cases, and even as you were saying, potentially getting it down to something that could fit in a car or as a camera or an iPhone or a smartphone, the algorithm is really what varies, and the algorithm in each of these use cases is embodied in a series of, I think you refer to them as programmable plates, right? You actually are hard coding essentially the algorithm in the design of the camera for that particular use case. How flexible is that set of programmable plates, and how hard is it to embody a new novel algorithm in those plates for a camera design?
Yeah. So the current generation is hard coded. That's why we're kind of limited to few use cases per device. Now, the next generation that we're building here is actually not hard coded. So that's kind of our, the secret sauce kind of making it work flexibly. That one does not have limitations on what algorithms you can run, or you can even run them successively. So you could run 50 algorithms successively after each other. And that's where it really gets interesting. So that's our Gen 2 camera. And the Gen 2 will be able to build let's say, do classifications on the fly. So let's say we just won an award last week or 2 weeks ago from NASA called Space to Soil, which was our use case was detecting illegal deforestation in the Amazon before normal satellites can do that because they're just too expensive and too slow to process this data. By the time you're done, the loggers have left, right? So our technology, we propose to put it in a satellite, a CubeSat, fly over. Anyways, the satellite is orbiting the Earth all the time. So at some point, you're passing the Amazon. So you can run an algorithm that just detects for canopy, right? So the missing canopy or not. Now, when the satellite flies over, so it flies further from the Amazon. Now it's going, let's say, a bit over the Atlantic. Now you can run, let's say, looking for ships, right? But you're not going to look for canopy on the Atlantic. You're going to look when you're in the Amazon. So doing that, you can reprogram it while it's in orbit and send it new algorithms. And the idea is that you can run, probably, I don't know what the limit would be, but technically unlimited amount of algorithms, basically on the firmware. And what the firmware does, the camera just adjusts the plates basically in a way that works for that particular algorithm. But you shouldn't have any limitation for that. The only limitation you have is wavelength. Basically, but you can do multiple wavelengths. You can do any wavelength. You just have to pick one, basically.
Interesting. And I mean, that sounds like as you continue to develop this technology, I mean, how close are you going to get to universal computing eventually? If you just sort of extrapolate out, if the programmable plates are infinitely programmable, then I mean, I would assume that's almost like an optical Turing machine, right? The tape's moving back and forth, right?
Yes. Yeah, in a way it is, yeah. But you have some practical limitations in the sense of each layer that you do introduces loss.
Okay.
You do not want to create, I don't know, you wouldn't recreate a neural network the size of ChatGPT, right? You have like hundreds of nodes and hundreds of layers, right? Because at that point you have introduced too much loss to make it interesting. And you do one processing at a time, when you're in there. So I'm not sure this is a fully Turing complete computer in that sense, but we could see it. I need to see how far, or maybe ask Saikat also how far we can get with in the
So it's
realm of
almost,
universal
I can
computing.
imagine looking back in the future and thinking this is as almost like the photonic Babbage difference engine, right? Where it's like it's a limited sort of form of a
Right.
proto classical computing
Yes,
device.
it could be.
That's really interesting.
It could be.
So okay. So I want to touch on before we finish up. You talked about the market research that you did at MIT, the QIR report, or quantum information report. That's really, I mean, it's really unique that somebody who's an entrepreneur in the quantum technology space also has that background with very broad market analysis and research. I'm curious because of that. I'm really curious about your perspective about sensing in particular. I mean, I can see why you chose sensing in this technology in particular. TRL4 is a much shorter runway, but from a public perspective or investors, policymakers, enterprise decision makers, sensing feels like it's still running under the radar. And so I'm curious on your perspective of like, what is needed to really hit the gas in terms of the potential for quantum sensing as a category? Is it more investment? Are there regulatory policy or is investment from the public sector? What's sort of the missing piece, I guess?
Yeah, I think one missing piece, honestly, the main missing piece is a bit PR, to be honest. So the quantum computing itself, I mean, took a long time to take off, right, from its origins. But one of the main thing around quantum computing is that everybody was kind of pulling on the same string of like, okay, this is a quantum computer, this is what I would be able to do. And then if somebody, I don't know, QERA comes up with something cool, then chances are the same thing can be used for Pascal or maybe even superconducting, right? So chances are, everybody's kind of pulling on the same string of saying, hey, here's quantum computing. Let's explain it to lots of people. Here's a McKinsey report. Here's a whatever, Deloitte, BCG report. People talk about it. If it's in the media, quantum computing is quantum computing. So people kind of get it. Quantum sensing suffers a bit from the fact that it's multiple things kind of come together. So it's not like if you believe, let's say, in magnetometry, you use some, then you're just thinking, all right, that's a useful application, but each technology has like different angles to it, and some are more meant for a medical device, and some are more meant for remote sensing. So each, again, you have to explain it from scratch, kind of, and why this particular device will work well in that environment. So that was kind of also my issue when I was fundraising or trying to explain it. You have to create your own narrative that explains this particular technology and why it helps. You cannot just tap on an existing narrative and say, oh, we just built quantum computers. I don't need to explain you what a quantum computer is. We are just better than the other guys because we have XYZ benefits. So you're kind of stuck in that narrative. And I'm not sure this is necessarily super easily solvable just by the nature of what this is. So you really have to stick with your narrative. But I do think in quantum sensing, we can do a much better job of both kind of explaining it with a more kind of unique narrative or unifying narrative across, and make it easier for people to understand why quantum sensing is interesting, why it's near term, right? All these kind of benefits of quantum sensing. Less complex, less capital intensive, more near term, real life applications that are very close or already being already applied and lived with, and push a little bit more around public funding and also VC funding, right? Because both are necessary. But I think that being said, the recent executive order just came out kind of a week ago or so on quantum, also mentioned specifically quantum sensing, and then directed, DOW, NASA, and so on to have, and DOE and others to give quantum strategy and quantum sensing, quantum computing. So for quantum sensing, particularly, we have seen a couple things that memos from departments that explain very well of like, hey, this is quantum sensing. We want these kinds of things, and we want to push it further. So that seems to gain more traction, which is very positive to see. Yeah.
That's great. Well, thank you so much, Johannes. This is really a fascinating conversation, a fascinating piece of technology, and I can't wait to see or hear about, I guess. I won't see images from it, but hear about what kinds of results you're getting from your camera. So thank you so much.
Well, thanks so much, Sebastian. It's a pleasure.
This episode was brought to you by Outshift, Cisco's incubation engine. The need for computational power is rapidly increasing in every sector. From drug discovery to material innovation to complex financial modeling, classical systems are reaching their absolute limits. It's time for a paradigm shift. The answer is a scalable quantum network built on open standards and vendor-agnostic architecture. By uniting distributed quantum devices, you unlock limitless computational power. Learn more about the Cisco Universal Quantum Switch at outshift.com. Thanks to Johannes for a conversation that did something I really value. It took a term that could be easily considered marketing gloss, a quantum camera, and walked us honestly through where the quantum information theory actually lives, where the photonics take over, and where the classical readout finally has to happen. The frog's eye analogy is going to stick with me for a while. The idea that you could give a satellite something closer to a reflex than a perception cognition loop is a genuinely different way to think about onboard intelligence. For the papers, the MIT Quantum Index report, the press coverage of Diffraqtion's emergence from stealth, and links to the related New Quantum Era episodes on quantum sensing and sub-Rayleigh measurement, head to the show notes. And if you want more of this kind of conversation, plus writing and analysis between episodes, sign up for the newsletter at newquantumera.com. If you're getting value from the show, the best thing you can do is subscribe wherever you listen and send this episode to one person who's still tracking only the computing side of quantum. Quantum sensing needs an audience. Thanks for listening. I'm Sebastian Hassinger, and this has been The New Quantum Era. Theme music by OCH. See you next time.